You know, that incredibly refreshing feeling of a breeze coming off a lake on a hot day? Well, that's evaporative cooling in action. Today, we're going to dive into the engineering behind this really old but super effective method of air conditioning.
I mean, think about it for a second. How can you possibly make air colder just by adding water? We're not talking about fancy refrigerants or complicated machines. Nope, just air and water. Let's unpack the science behind this little bit of magic.
And the secret? Well, it's all in a device that looks something like this. The whole point is to get as much water surface area exposed to the air as possible. You want to create the perfect conditions for evaporation, because that phase change from liquid water to vapor is what powers this entire cooling process.
Okay, so what's really going on here? Let's get into the nitty-gritty of the physics and see how this actually works.
So, in simple terms, you take warm, dry air that's kind of thirsty for moisture, and you blow it across a wet surface. That air just soaks up the water vapor. But this process isn't free. It needs energy, a very specific kind of energy.
And that brings us to the absolute core of this whole thing. See, we're dealing with two types of heat here. First, there's sensible heat. That's the stuff you can feel, what you measure with the thermometer. Then there's latent heat, which is kind of like hidden energy that gets absorbed when water turns into vapor.
And this right here is the key. The energy needed for that evaporation, it gets pulled directly from the air itself. The air literally gives up its sensible heat, the heat you feel, to power that phase change. So what you get is this brilliant trade-off. The air gets more humid, yeah, but it also gets noticeably colder.
Now, talking about this is one thing, but as engineers, we need to see it, we need to measure it, and for that, we're going to turn to our most powerful tool for dealing with moist air.
Ah, yes. If you're in engineering, you probably know this chart well. It's the psychrometric chart. This is our go-to map for understanding everything about moist air. And with it, we can perfectly track how the air's properties change during evaporative cooling.
Now, look closely at the path the air takes on the chart. See that? It's not a random curve. It's a straight path that perfectly follows a line of constant wet bulb temperature. This is a huge clue. It tells us something really, really important about what's happening with the energy.
So, what's this path telling us? Well, first, the dry bulb temperature drops. The air gets cooler. Check. The humidity ratio goes up. The air gets more humid. Check. But here's the kicker. The wet bulb temperature and the total energy, or enthalpy, stay pretty much the same. It's what we call an adiabatic process. We're not losing energy, we're just changing its form.
Seeing it on a chart is great, but to really design systems, we need to speak the language of engineering, and that means math. So let's look at the equations that actually govern this process.
So, to get to our main equation, we're going to lean on two of the biggest laws in physics, the conservation of energy and the conservation of mass. We'll take them one by one and then put them together to get the full picture.
Okay, step one, energy. You know the rule, right? The first law of thermodynamics says energy can't be created or destroyed, it just moves around. For our system, that means the total energy of the air and water going in has to equal the total energy coming out. We call this total energy enthalpy, and it stays constant.
Next up, the water. Same principle. Mass is also conserved. So, the amount of water vapor in the air coming in, plus the liquid water that evaporates into it, has to equal the total amount of water vapor in the air going out. It's really just simple accounting.
And when you put that energy balance, that mass balance together, you get this. This is our governing equation. This is the tool that lets us precisely calculate how much cooler the air will get based on how much water we evaporate. This is how we design real systems.
All right, enough theory. Let's see how all this comes together in the real world. Where do you actually find evaporative cooling in action, and what are the big things you need to remember?
You see this principle everywhere, especially in dry climates. Those residential swamp coolers are a classic example. But it's also a workhorse in huge industrial settings, in agriculture for cooling greenhouses, and even in standard HVAC systems for adding humidity. It's incredibly versatile.
Look, if you remember just one thing from all this, make it this. Evaporative cooling is a brilliant, real-world example of energy conversion. It's a simple, elegant, and super efficient way to trade that sensible heat you feel for latent heat you don't, all to make a space more comfortable.
So there you have it, the science, the chart, the math, and the real-world uses of evaporative cooling. Now the ball's in your court. With this knowledge, where do you think this powerful and pretty sustainable technology could make a difference? The possibilities? Well, they're endless.
Thanks for joining me.